Hello and welcome. We're surrounded by this invisible power that runs basically everything in our lives, from the phone in your pocket to the lightning storm outside. But what is it really? Well, today we're going to pull back the curtain on the invisible architecture of electricity itself. We're going to break down four huge concepts: charge, force, field, and potential. Let's jump right in.
So let's start with a kind of a strange question, right? What on earth could a bolt of lightning have in common with a quiet, invisible force of gravity that's holding you in your seat? One is this brilliant, chaotic flash of energy, and the other is just there. Well, the answer is that they are both described by almost identical laws of physics. And if you can understand one, you're well on your way to understanding the other.
And this right here is the core idea for our entire journey today. For gravity, the thing that makes it happen is mass. For electricity, the source is something called charge. But here's the big twist. Gravity only ever pulls things together. It's always attractive. Electricity, though, it has a dual personality. It can pull things together or it can push them apart. And that one little difference, well, it changes absolutely everything.
So if we want to get a grip on electricity, we have to start right at the beginning with the source of it all, electric charge. You can think of it like the fundamental source code for every single electrical thing you've ever experienced.
So what is charge, really? Well, it's just a basic property that certain particles have, like protons and electrons. It's just like how things have mass. And if a particle has charge, it can feel an electrical push or a pull. We measure this property in a unit called the coulomb. Now, the amazing thing is that all of charge's behavior comes down to three incredibly simple, unbreakable rules. First, if charges are the same, like two positives or two negatives, they push each other away. They repel. Second, if they're opposites, a positive and a negative, they pull towards each other. They attract. And finally, you can't just make charge appear out of nowhere. You can move it around, sure, but the total amount is always conserved.
And this impossibly tiny number you're looking at? That's it. That's the smallest packet, the smallest Lego brick of charge that exists in nature. It's called the elementary charge. Every single proton has exactly this much positive charge. And every electron has this much negative charge. Any amount of charge you ever find is just a whole number of these little packets added together.
Okay, so we've got a handle on what charge is. Now let's get into what charge does. And that brings us to the next big idea, the electric force. This is the actual interaction, the real push and pull that happens between charged things.
And this really gets to the heart of it. We said it before, but it's so important. Mass only attracts other mass. That's all gravity does. But because charge comes in two flavors, positive and negative, the force it creates can go both ways. This allows for a way more complicated, way more interesting world than gravity could ever build on its own.
So how strong is that push or pull? Well, this beautiful equation, Coulomb's law, tells us exactly that. It says the force depends on the size of the two charges, Q1 and Q2, and, this is key, it gets weaker the farther apart they get. And not just weaker, but weaker with the square of the distance. So if you double the distance, the force drops to a quarter of what it was. It fades away really, really fast.
Now look at this. Just look at the similarity here. Coulomb's law on the right has the exact same structure as Newton's law of gravitation on the left. It's uncanny. They're both what we call inverse square laws. So if they look the same, why is the electric force so much stronger than gravity? Well, it all comes down to those constants, G and K. The gravitational constant, G, is a tiny, tiny number, but the electric constant, K, is absolutely enormous in comparison.
All right, so talking about forces between two specific objects is fine, but what if we want to describe how a single charge affects the empty space all around it? For that, we need a new idea, and it's a powerful one: the concept of a field. So, an electric field is basically a map of influence. It's a property of space itself that gets created by a charge. Then, any other charge that wanders into this region will suddenly feel a force. You can think of the field as a set of invisible instructions, telling any other charge which way to go and how hard it's going to get pushed. And look, the parallel with gravity is just impossible to ignore. Here on Earth, the force of gravity on you is your mass, m, times the gravitational field strength, which we call g. While in electricity, it's the exact same idea. The force on a particle is just its charge, q, times the electric field strength, E. The field is simply the force you get per unit of stuff, per kilogram for gravity, and per coulomb for electricity.
But this field is invisible, right? So how do we picture it? We use something called field lines. Now, these lines aren't real, they're just a tool, but they show us two really important things at a glance.
They show us the direction of the force on a positive charge, and they show us the strength. Wherever the lines are bunched up close together, the field is really strong. Where they spread out, the field is much weaker.
And the patterns these lines make are actually pretty intuitive. Since a positive charge would push away another positive charge, the field lines always point away from positive sources. A negative charge would pull a positive charge in, so the lines always point towards it. And if you have both, the lines flow gracefully from the positive charge and land on the negative one.
Okay, this next concept can feel a little abstract at first, but trust me, it's one of the most useful ideas in all of physics. It's all about the energy a charge has, not because it's moving, but simply because of where it is in space. This is electric potential.
Let's go back to gravity for a second. Imagine you're holding a cricket ball high up in the air. It has potential energy, right? Not because it's moving, but because of its position in Earth's gravitational field. If you let it go, that stored energy turns into the energy of motion. Well, the same exact idea applies to a charge in an electric field. So how do we measure that sort of electrical height?
We measure this electrical height with something called electric potential, but you definitely know it by its more common name, voltage. Now here is the absolute key insight. Voltage is not energy. It is potential energy per coulomb of charge. This is so important. It means voltage is a property of a location in the field. The voltage is there whether you put a charge there or not.
Okay, the best way to visualize this is with a map. Think of a topographic map of a mountain. You see all those contour lines, right? Every single point on one of those lines is at the same exact elevation. Well, equal potential lines in electricity are exactly the same thing. Every point on one of these lines has the same electrical height, the same voltage. And just like walking along a flat contour path on a mountain, it takes no work to move a charge along one of these lines.
So let's put the sequence together, step by step. First, a source charge exists, and it creates an electric field in the space around it. Second, because of that field, every point in that space now has a specific value of electric potential or voltage. And third, only when you place another charge at one of those points does it now have electric potential energy. It's a beautiful chain of cause and effect.
All right, we've gone through the 4 core pillars of this invisible world. We've talked about charge, force, fields, and potential. Now, let's tie them all together and see how they form one single complete picture.
This table is really your ultimate cheat sheet. Charge is the source of it all, measured in coulombs. Force is the direct push or pull between charges, measured in newtons. The field is how we describe the charge's influence on the space around it, and potential, or voltage, describes the energy of a location within that field. 4 concepts, one single reality.
And this is the most important takeaway of all. Charge, force, field, and potential aren't 4 different things happening. They are 4 different lenses, 4 different ways of looking at and calculating the effects of the exact same underlying interaction. Depending on the problem you're trying to solve, one lens might be more helpful than another, but they're all describing the same fundamental truth.
And that brings us to a final, mind-bending thought. We've established that the electric force is astronomically, ridiculously stronger than gravity. So why is it that when we look up at the night sky, at planets, stars, and entire galaxies, gravity is the one running the whole show? Why aren't planets repelling each other? It's a question that really gets to the very heart of how these forces shape our entire universe. Thank you for joining me.